Okay, so here we have two chlorine atoms joined together. What does that form? A chlorine molecule, yes. And here we have, let me see what order it's written in. We have a single pair of electrons. In other words, 2 electrons. When we have a single pair of electrons that are shared, what do we call that? We call it a single covalent bond. Why do the chlorines look so happy and serene right now? Because what? They're stable. They have that full outer shell, which makes them super stable. So 2 chlorine atoms come together and share their electrons to form a molecule of chlorine. And this way, each atom will have how many electrons in its valence shell? 8 electron in its valence shell. And because we have 8, that is a complete octet, and that is very stable. As a single pair of electrons is shared between them, this bond is known as a single covalent bond. And we very often represent a single covalent bond by a single line between the atoms. So if I draw a Cl, what do I draw before I draw the next Cl? Just a line, okay? Those 2 electrons there represented by the line are a single covalent bond. Okay, how many electrons does oxygen have in its valence shell? 6. How many more does it need to complete its octet? It needs 2 more to complete its octet. Remember, that means 8 electrons. So it will share 2 of its electrons with who? Another oxygen atom, yes. Oh, that's so weird. The picture's different. Huh. Oh well. Okay, so now instead of having 2 oxygen atoms, we have 1 oxygen molecule. How many pairs of shared electrons? 2 pairs. And by 2 pairs, we mean, of course, 4 electrons. Now, because we have 2 pairs, it's no longer a single covalent bond, it is a double covalent bond. And in fact, we don't have things like double ionic bonds, so we're going to start at some point to just refer to it as a double bond, okay, and leave out the word covalent. But we'll put it there for now because it's brand new. When 2 oxygen atoms come together, they each share 2 electrons. So they both contribute 2 electrons to that double bond to complete their what? Octet. Since they share 2 pairs of electrons, there is a double bond. Between the oxygen atoms. And how do we show that? What do we draw between the 2 O's? We draw 2 lines. So the 2 lines here represents 2 shared pairs of electrons. And then in our final atom here, we have our final molecule, we have a nitrogen molecule. So 2 nitrogen atoms, and they share a triple covalent bond to form a molecule of nitrogen. And how would we represent 3 lines? And that's 3 shared pairs of electrons. Okay. And you guys now have enough information to spend a few minutes Oh, this is a nitrogen molecule. We have 3 shared pairs of electrons. And this is a triple covalent bond. You want to spend a couple minutes doing the exercises? Yeah? Okay. Mackenzie's here, Caleb's here, Nathan is here, Alyssa's here, Tomas is here, Evan is here, Connor's here, Zenny's here, Nina's here, Daria is here, James is here, Ace's here, Leon's here, Peter Roy is away, Jessica Z, Sky, Isla, Haley, and Reed, Kyan, Ella, Stephen, Matthew, Rena, Jude. So I've had a couple people ask, what's up with the X's? The X's just show an electron. It's just to be able to distinguish the electrons on one fluorine from the electrons on a different fluorine, okay? How are we doing? Does anyone want more time? Totally good if you do. We're ready? Okay. Okay, we're gonna look at covalent bonds in a little more depth. Oh, okay, we'll give you another few minutes. Yeah, no problem. Okay, so before we move on, I did want to make sure that we're all getting these answers correct. I know you have an answer key, but let's just double check, especially number 6 and 7. Okay? It says, how many electrons are shared between the carbon and the hydrogen? We have one line, so how many electrons is that? 2 electrons. Over between the carbon and the nitrogen, how many electrons are there? 6, because there's 3 lines, 2 electrons each, so there's 6 electrons. And then if we look at these 2 fluorines, this fluorine has 7 valence electrons, and this fluorine also has 7 valence electrons. So if we think about it this way, it's like we've got a hole here, and we've got a hole here. Wouldn't it be nice if they could help each other out by filling those holes, right? So what we're going to do is we're going to overlap that middle part, and we'll have this electron here, and this electron here. So that's the overlapping bit. Okay. And then we have the rest of the electrons all the way around the outside. And the same thing on the other one, we have the rest of the electrons all the way around the outside. Now you'll notice I dropped the inner shell. It is okay to do that, okay? You can show only the valence shell if you want to, because it gets, you know, if you're doing chlorine and you had to show them all, you'd be drawing 3 rings. So it is optional to show the inner shells. Okay? If you need to draw the inner shells to figure out how many valence electrons there are, that's perfectly good. Do it. Yeah? But if you can figure out how many valence electrons are on that outer shell without drawing the entire Bohr model, you can just go straight there. Okay? So that's up to you what makes it easier. Okay? All right. So, ionic bonding. Super well for what types of elements? Who gets bonded by ionic bonding? Metals and nonmetals. And not only is it a metal plus a nonmetal, but it is a cation plus an anion. And if we were to draw that, how would you draw a cation? You're not going to draw a cat, there's a hint. You can just draw a circle, and what would you put in it to show your cation? A plus. And you would draw the anion by drawing a circle and a negative. And the ionic bond is just the attractive force between the positive and negative ions. So that's what an ionic bond is, and we've spent the last couple days talking about that. Okay. But when we have compounds that are made exclusively from nonmetals, so nonmetals only, Ionic bonding fails completely. It does not work. One reason nonmetals always try to gain electrons. They're electron takers. Can you imagine what would happen if you tried to have one negative thing with another negative thing? What would they do to each other? They would repel. And in fact, that repulsion could lead to an explosion. So we're not going to have that. Nature says, no, I don't like having two negative things beside each other. So instead, nonmetals need another way to bond. So instead, they share their electrons. Okay, and you can see here, this is like the Bohr model here. And do you notice that you have a positive charge here and a negative charge here? What do positive and negative do? Attract. What is that positive thing in the middle of the atom? That is the nucleus. So you have a positive nucleus. Okay, and in the other atom, you also have a positive nucleus. And in between the two atoms, what are these things here? Those are the shared electrons. And of course, the shared electrons are negative. So positive attracts to negative. So the positive nucleus attracts the negative shared electrons. Could I draw more attractive forces on this diagram? Probably. Where would those attractive forces go? Tell your partner, show them on their diagram where those attractive forces would go. So I've drawn some here and here. Where else could we draw attractive forces? Yeah, right on the other side, absolutely. So we could draw those attractive forces here and here. That attractive force is the covalent bond. Now, here's something interesting to notice. An ionic bond is an attractive force between a positive ion and a negative ion, positive and negative. So we have an attractive force between positive and negative. That is an ionic bond. Down here, look what we have. We have an attractive force between a positive and a negative. So really, they're just different types of the same attraction. In the ionic bond, you've got ions that are attracting. In the covalent bond, you have the nucleus attracting the shared electrons, but it's still all just positive attracting negative. So all bonds are caused by positive attracting negative. Yes. All bonds are caused by positive and negative charges attracting each other. And then we have the electron cloud model. And you remember how the electrons, they're not actually like on a shell. They're really buzzing around like crazy hyperactive flies, okay? And so you end up with electrons appearing here and there 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 and there. And if you took pictures over time, eventually you'd end up with a picture that looked like what we have there, okay? And you can see there's a lot of density of those electrons in the middle, in between. Okay, so this is just a picture of what we've shown above, just prettier than what I've drawn. Okay, so we have attraction between the nucleus and the shared electrons, and that attraction is the covalent bond. Yes. Yeah, for sure. Now, if you're not interested in this, you can just put your head down for a moment and ignore me. We're going to talk about electronegativity here, all right? And so if you're like, okay, I'm not doing electronegativity, just have like a little rest, okay? So the real reason that nonmetals share electrons rather than giving and taking like in ionic bonding is as follows. Nonmetals have similar electronegativities. That is the ability to pull on electrons within a bond. So rather than one atom pulling strongly, like a metal, and the other one pulling weakly, or I'm sorry, like pulling strongly like a nonmetal, so it's the nonmetal that pulls strongly, and the other one pulling weakly like a metal, both nonmetals pull relatively equally, which means that they share their electrons. Let's imagine that I have an electron here. Do I have a volunteer who would like to hold the other electron? Yes, excellent, fun. Okay, so we're going to start off, and you're going to be the non-metal. So are you good at pulling or are you bad at pulling? You're good at pulling. Okay, so if he's a non-metal and I'm the metal, okay, we're going to try and grab each other's electrons. Okay, you're good at pulling, I'm bad what charge am I? Positive, and what charge is he? Negative. So that's an ionic bond, okay? Now for a covalent bond, now I'm going to stop being a metal, I'm going to be another non-metal. Maybe you're fluorine and I'm chlorine or something like that, okay? And now we pull equally. Yeah? So that's a covalent bond. We're both pulling on these, and that's what sticks us together, okay? So actually, I would really, really recommend, I'm not going to force you, but I would really recommend, that you with your partner get yourself 2 pencils, 2 pens, 2 something, and form an ionic bond, and then form a covalent bond, okay? So you can go for it. If you choose not to, I'm not, like I said, I'm not going to force you, but it's a good idea. Here, have some pens. Because I'm going to know you're like this, right? Alrighty, so covalent bonding. What do we make? When atoms bond covalently, we make molecules. So here's 2 hydrogen atoms sharing 2 electrons. We get a hydrogen molecule. Here we have 2 fluorine atoms. They are sharing 2 electrons, and we get a fluorine molecule. Here are 2 oxygen atoms. I know I haven't drawn both of them. I've only written 2 there, but can you imagine there's 2 of them? Okay. One goes on one side of the carbon and shares 2 of its electrons, and the other goes on the other side of the carbon and shares 2 of its electrons, and the carbon here shares 2 with the one oxygen, and it shares 2 with the other oxygen. Yes? Yes. So if I wanted to draw the hydrogen molecule and I put an H here and an H here, what would I draw in between them? One line, right? If I have my fluorine, what would I draw in between my 2 fluorines? One line, because there's one shared pair. Now if I have carbon dioxide, C is in the middle, O is on the one side, O is on the other side. 2 lines on each side, 2 shared pairs of electrons. Now I've got, in my next one, I have a carbon, and you can see that it would be really nice to share with that fluorine. How many fluorines am I going to need to make carbon stable? 4. I'm going to need one on the top, one on the side, one on the bottom, and one on the other side. So that would be C, F, 4. And if we want to write our symbols for these, do you guys remember, how would we write the symbol for carbon dioxide? We would write it as CO2. What do we call that little number down at the bottom? Subscript. What does it tell you? The number of those atoms, yes. So what would the formula for carbon tetrafluoride be? This one here, what would be the formula for that one? CF4. And you know how di means 2, so we have carbon dioxide, 2 oxygens. What do you think tetra means? 4. Tetra means 4, so we have carbon tetrafluoride. You're not responsible for knowing these prefixes in this unit, they will be in the next unit. So a molecule, it is neutral. It is made of nonmetals, and it's held together by covalent bonds. Now you have to think back. If I have a formula unit, what is a formula unit? See if you can remind your partner, what is a formula unit? It is the smallest piece of an ionic compound that you can have. Yes, but it has to be an ionic compound. Yeah. So a formula unit, if you're having trouble finding it, which you might be having trouble finding it, is a single unit of an ionic compound. So it would look like, what would we draw for a formula unit? 1 negative and 1 positive. So we would have 1 positive and 1 negative, okay? If I have an ionic compound, what's this structure called? This is a crystal lattice. And if I took just 2 of those, the positive and the negative, that would be a formula unit if I could take just 2 of those out, okay, the positive and the negative. Why is that not a molecule? Remember, we just talked about molecules. Molecules are made of 2 or more nonmetals bound by covalent bonds. Not quite. Not quite. What are ionic compounds made of? Metals and nonmetals, but what are molecules made of? Nonmetals and nonmetals, okay? So it's not a molecule because an ionic compound is a metal plus a nonmetal. Formula unit is ionic is metal plus nonmetal. And molecules are only nonmetals. I really have not left enough room for this. So I'm going to put it on the next page. So we know that a formula unit contains a metal and molecules are only non-metals, so a formula unit cannot be a molecule. There's another thing that tells us that a formula unit cannot be a molecule. What else does a molecule have? Yes? Yeah, the molecule is always covalent bonds, and a formula unit is held together by ionic bonds. Okay, and on the next page, we actually have like a picture of why it doesn't qualify. We've got that formula unit of sodium chloride, and we've said it contains both metals and nonmetals, but molecules are only nonmetals. And ionic bonding holds a formula unit together, but covalent bonding holds a molecule together. Even more so, if you want to, a formula unit is made of oppositely charged ions, whereas molecules are made of neutral atoms. And a formula unit never actually exists on its own. It's always part of a larger crystal lattice, but a molecule, H2O, can just be by itself, no problem. So the number of holes in the valence shell will generally determine how many bonds an atom can form. So if we look at hydrogen, this is shell number 1. How many electrons maximum in shell number 1? Maximum 2 electrons. So how many holes are in hydrogen? 1 hole in each hydrogen. Now carbon, its outer shell is shell number 2, which has a maximum of, oops, I shouldn't write over here because, oh no, that's okay. It'll be fine. That's a maximum of 8 electrons. So how many holes, Nathan? How many holes are in the carbon atom? Outer shell. 1 up here, 1 over here, 1 over here, and 1 over here. So if we were to show these guys all sharing, I'm going to take this electron from hydrogen. Do you see the one I've colored red? One right here. I've colored it red and highlighted it yellow. I'm going to put it here. Okay? And that means that I now have hydrogen sharing with carbon. Okay? I'm going to do the same thing for the hydrogen on the top. I'm going to put its electron here. You'll notice I'm not very good at drawing circles, so you know, if you're worried about your circle drawing skills, don't be. And on the right-hand side, we've got another hydrogen here, providing 1 electron. And on the bottom, we have another hydrogen here, providing another electron. And if anyone is interested, this compound is known as methane. Have you heard of methane? Yes, cow farts. And it's the same gas that comes out of here, out of our gas pipes, that allows a flame, okay? And we'll be doing like a Bunsen burner activity early next week, okay? Yep. All right, so that is methane. And what would the formula for methane be? CH4, yes. Here we have holes. Here's a hole. How many holes does nitrogen have in its outer shell? 3. 1, 2, 3. So we're going to take hydrogen's electrons, and hydrogen also has 3 holes, or well, each one has 1 hole, and we'll fill them in. 1, 2, 3. Each of those came from a hydrogen. And this one is N. And then what would the rest of the formula be? NH, how many? 3. And the name of this compound is ammonia. Yes, ammonia. So if you've ever used Windex, okay, it's in Windex. Ammonia like a what? That's pneumonia, okay? Ammonia is not the same as pneumonia. Pneumonia is a disease. Okay, different things entirely. So methane, if we want to get all scatological about it, methane is in cow farts, and the smell of pee is often due to the ammonia in it. How lovely is that? Just to share that with you to make your day a little brighter. Yes? Cow farts and pee. Yep. Urine. All right, and finally, here's a compound we should all be familiar with. What have we got here? We got water, H2O. And we have how many holes in the oxygen's outer shell? 2, and that's why we have 2 hydrogens bonding in there, right? We've got this electron goes here, this electron goes here. And if you turn that the right way, who is it? Mickey Mouse. Yes. That's a very good question. Short answer is I don't know. Longer answer is the NH4 plus ion is the ammonium ion, and that's how it's written. It may be that it's just been written that way since forever. I don't know. I kind of there was something about an explosion in 1972, and I did not catch that. So I was like, what? What? That was a long time ago. I was only 1 year old. In 1971 and 1972? So homework is page 53. It's not very much, but if you look back at your notes, you should be able to find the answers. 53. Oh my gosh, I keep forgetting to give you guys your tests. Every day, I think I should give you your test, and then every day, I've forgotten to give it to you. So if you would like your test, if you want to have a better look at it, you can come in, you can have it back again next day. But if you just want to see your grade, you can see it today. Listen for your name, hand it back when you are done. What are you going to do with it when you're done looking? Hand it back. Caleb, Isla, Dario, Kita, Ziv, Izzy, Reed, Sky. Thank you. Haley is not here. Ella, Jessica, Alyssa, Nima. And if anybody wants to come in and do corrections on their test to improve, please come and see me during flex. Tomas. Roy is not here. Cassie. Oh, we already talked to Cassie. Who have I got here? Tomas. Kyan is not here. Reina. Nathan. Thank you. Thank you. Thank you. Mackenzie. Thank you. Jude. Connor. Connor. Jude. Leon. Steven. Can I hand it in? Yep. It's right here. Okay. Yeah.
Thank
So
you.
that is just we're on the scale because we're doing proficiencies instead of numbers. Yeah. How is it emerging? Because it covered about maybe a quarter of the material. Yeah, and about a quarter of the material. Yeah. So the curriculum has like many different things, and you've done some of them, but not all of them. And that's fine. Being emerging is perfectly good. Right? Yeah. Yeah. Thank you. Yes. Thank you. Thank you. Thank you. Thank you.